All right. Last time we took an exam, but the time before that, we talked about some content. We talked about how to make context-free grammars. Who can recall what were there any rules associated with context-free grammar productions? What? What were any restrictions that we had on context-free grammars?
Relax the restriction that a non-terminal must appear only on the left or right side.
Yeah, we basically said everything that we restricted for regular grammars, we're going to release those restrictions and you have basically full creative control. There is an issue with full creative control. And that issue ends up being efficiency. So we need some way to intelligently restrict context-free grammars, not so that we can only produce those languages, but so that we can start answering some important questions in a reasonable amount of time. So we're going to start talking about a couple of those problems and some potential ways that we could look at that, and then the issues that arise when we do that. So here were some examples of some context-free grammars. We looked at some of the derived strings, and then we saw that we could map them directly onto things like mathematical parentheses, or from a more programming perspective, curly braces that now could represent any level of nested conditionals or loops or methods. And that was really cool. So context-free languages include things like control structures in languages. The next thing we're going to start wanting to talk about are how we're actually going to parse a context-free grammar. The most important question that we can ask and answer about a grammar is, given a query string, can that grammar produce that string? Is that string in the language? We talked very briefly about the concept of an ambiguous grammar, which is, if that was the case, then given a particular input string, there were multiple different ways to derive that string, which can create an issue. We know from search theory, I don't know if that was covered in algorithms or not, but if you have a single goal rather than multiple goals, then the process by which you go search for that goal is more streamlined. You're not looking for a goal, you're looking for the goal. So here's an example grammar. And we had this couple different ways to produce AAB. We saw this on Thursday, I think. And because of this, we want to be able to determine there is a correct way and an incorrect way to derive AAB. It doesn't matter which one of those ways is correct and which one is incorrect. We want to force a particular order. So if we continuously replace the leftmost non-terminal, then we're doing what is called a leftmost derivation. So an example for this is when we derive SAB, the first thing we're going to do is look at this A and replace it with AAA. Always starting with the leftmost non-terminal, we're going to do that replacement. This A now becomes the lambda, but we're always looking at the leftmost non-terminal. As soon as there's only one, it doesn't matter. Whenever there are multiple, we're always going to be looking at the leftmost. On the bottom here, we're doing a rightmost derivation, where given there are multiple non-terminals, we're going to find a production for the rightmost non-terminal first. Again, it doesn't matter which one of those you use, as long as you are consistent, then it becomes such that there is only one way to derive a particular string. The search space is still too large, but at least there becomes a single way to derive a particular string, which removes the ambiguity part of the grammar. Kind of. There's still one lingering issue. So you can think of ambiguous grammars as having different ways to interpret and produce the string. And if you think about this from a compiler's perspective, even if it ends up doing the same thing, maybe there's a difference in efficiency between one compiler and the other for the same kind of problem, which would mean that there is one compiler that you want to use for a particular problem because it has more efficient parsing for this particular kind of problem, but you know, when you write in the language, call it Java, that you should be using certain compilers for certain kinds of constructs that you produce that's based on the grammars for Java that's different between the different languages and the different compilers. It explodes the complexity of managing a language and learning how to code. So this creates some massive unnecessary headaches that we will further explore when we actually are looking at how a compiler works. Like I mentioned, the grand scheme of this course is we're going to be going through a lot of the theory at the beginning, and then we're going to apply that theory to the actual process that compilers go through in the last few weeks. All right, so here's a grammar. Let's go through this process and provide a leftmost and rightmost derivation for AB, BBB. So you're going to start with the start non-terminal, and then you're just going to replace each non-terminal in a leftmost fashion or a rightmost fashion. Since there's only one production, I guess there are two productions for B. You'll have to choose whichever one helps you to be able to produce the desired string. hopefully this is what people got for a leftmost derivation. We see that we only have one option for what we can do with the start non-terminal, so we'll produce lowercase a, capital B, that's the only thing we can do. If it's leftmost, then we need to resolve that A first. There's only one thing an A can do, become B, capital B, B, so we do that. We then need to resolve the first B, and it actually does not matter which of these B's turn into the A and which turn into the lambda. So you have a couple different ways that you could do this. This is just one such way. And similarly with a rightmost derivation, you still start with the same start non-terminal, producing the same only thing it can do. But then that B becomes a lambda. Note that it does not have to. Again, we're going to be producing two B's anyway. One of them needs to become A and one of them needs to become lambda. So there are still two ways you can do this. Neither one is more correct than the other. Questions on leftmost and rightmost derivations and how they can produce the associated string? So this is kind of the logical way to do it. You're just directly applying the grammar's rules. There's a bit more visual way to do it as well, and we call these parse trees. I've hinted at what this might look like before as we've gone over some of the examples of this, but let's get a more formal version of it and then do an example. So you can show a derivation with a tree structure as well by turning each non-terminal into and having children based on each symbol that that non-terminal expands to according to one of its productions. Once you draw out this structure, you will continue to expand the non-terminals. And that way, every time you reveal a terminal, it becomes a leaf in the tree structure. And every time you reveal or uncover a non-terminal, it becomes an internal node in the tree structure. So all leaves are terminals. And then once you have this process of a tree in front of you, what process would we go through in order to get the derived string? How could we actually print, given this structure, how could we parse the structure to print out the associated string? What procedure would we use? Where's the first terminal in the tree structure? Yeah, the leftmost leaf node. If we were to get there from the root node, how would we do that? Leftmost childs, leftmost childs, leftmost childs, et cetera, et cetera, et cetera, until you get there. Where's the next one?
Right after that.
The next leftmost, is it necessarily at the same level? No, but there's something that we've seen maybe in.
Depth first.
Yes, it's a depth first search. So note that the way that you've done this before is probably with binary trees. And there's no guarantee that a production only produces two total terminals and non-terminals. So you may end up with nodes that don't have the same number of children. And especially not necessarily two children. Because if we go back to a grammar example. Like this internal node, the S, would have 3 children. This internal node, the A, would have 3 children. This internal node B would only have 1 child. So depending on the production that you're doing, the branching factor of the tree will vary of each internal node. But that doesn't matter. We still use the depth first search rules that say of all of our children, recursively call them from left to right. So let's do an example. We'll use the same grammar, construct a parse tree for the same string. Note that we no longer care about leftmost and rightmost derivations necessarily. A parse tree will just be one such way of deriving this string. And maybe there are multiple such parse trees. In this case, there will be two different parse trees that we can use. But the concept of leftmost and rightmost derivations kind of goes away when you're constructing a parse tree.
How do we handle the case of B equals A or lambda? How do we handle the or?
Have a choice. Some such parse trees will lead to the string A, B, 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 in which case it's a good parse tree. Some of them will lead to a different string, in which case that's not a good parse tree for generating this particular string. So you have kind of you have a choice at that point. So I said that it removes the concept of left and right most derivations, but it does not remove the concept of there may be multiple parse trees where different choices of A and lambda, if we look back at the last example with this. When we decided that this B was A. We said that this B was A, and then that further expanded. And that this B was lambda. We very easily could have made the opposite choice, where this B is lambda and this B expands. Because they both produce the same string. So because of that, those choices, there will be two different parse trees that work for this.
Okay.
If you find one such parse tree, see if you can find the other. That should just be the A to B or A to lambda. And then going with it and choosing the other one. So two different parse trees that will produce the same string. Parse tree. They have a parse tree. No. Two parse trees, 2.5 parse trees. 3.5, 4.5. Is anybody stuck producing their parse tree? A little bit more time. For those of you who are done, you can check your answer. This is one of the two possible parse trees. Where is the logic in this parse tree where we could have generated the other parse tree? Where would that switch have been made?
It'll have the B on, or the first B just goes straight to lambda.
Yeah, so this B can go to lambda, this B can go to an A and derive the rest of it. But let's take a look and see how a depth first search produces the string A, B, 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 B. So if we're starting here, we would recursively call this, this, and this. We're gonna resolve this first, so we're gonna go here and say, for all of your children, we're gonna do kind of a node left, right printing. Have we seen that in data structures or algorithms where if you have a different tree structure, you have different processes, different ways of doing that? So if we do a NLR traversal, we print the value of the node only if it's a terminal, so it actually doesn't matter if it's NLR or LNR, because the only time we're getting to a terminal, it won't have any children. So you don't print any non-terminal. So we'll go to the left. And we will see the A, which produces this A. Back to S, the next thing we're gonna do is expand and explore this child. Since this is a recursive procedure, we're going to explore this before we go back to this. So for this, we're gonna generate all of its children and explore them from left to right. So we first get this B, so let's just kind of cross off the nodes that we get to. We've explored that B, which represents that B. We come back to the A, we go down here, we get nothing. We don't print anything if there's a lambda as a terminal. We come back, we explore here. That's this B. We go back to the A, we go back to the S, we explore this child. This only has one child, so we go there, we do this in this order. So this becomes the next B that we look at, which becomes this B. We explore down, get another lambda, backtrack to this B. Generate that. And we're done, back, back, back. We've seen every child, we've explored every node in the tree structure. So it's just doing a depth first search traversal over all of the leaves and printing any non-lambda terminals that we run across. Questions on this? So do note that this helps to determine what productions were used, but it does not tell you the order in which they were applied. So it doesn't tell you if this is a leftmost or a rightmost derivation, because you could use either a leftmost or a rightmost derivation, depending on whether or not you parse the structure from left to right or right to left. You generate that same parse tree if you did a leftmost derivation, in which case you'd just be figuring out, all right, what does the S generate? What does the A generate? What does the B generate? What does this B generate? What does this A generate? What does this B generate? Versus a rightmost derivation would start with the S and then go to the B first, and then the A and the B, and then back this way. So the leftmost versus rightmost is not apparent within the parse tree. What does help is the way that it's programmed. If you do left to right child recursion, you get a leftmost derivation. If you do a right to left child recursion, you get a rightmost derivation. All right, now that we have the ability to produce this in either drawing out productions or in drawing a parse tree, we can start asking the membership question. The membership question is an incredibly important question. I would argue it is the most important question that we've asked so far. So we always want to answer, given a string, so A, B, 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 B. Is it in the language of the grammar? Think for a second, how could we answer this question? You have a grammar, you have a query string, you need to be able to say yes or no. This grammar can generate this string. Well, we just kind of sort of did that, right? We at least said with a particular query string, draw a parse tree for it. And it was possible, mainly because this grammar was incredibly simple. But if we could possibly generate all leftmost derivations from the grammar and just keep generating and generating and generating and generating, one of those derivations would eventually match the query, as long as we had some way to terminate the process or determine whether a particular branch we were going down produced a string so far that was longer than the query string. So when we have A, B, 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 there are 5 non-terminals there for the string. If at any path we generate 6 non-terminals, since there's no rule in a grammar that can remove terminals from a generated string, we would terminate that branch and say, all right, there's no way this branch or any of its children could possibly derive the string, the query string. Does that make sense? There's no way that once we've created 6 non-terminals, or 6 terminals, that we could generate a query string of 5 terminals. So we would stop that process, go back through the recursion, and find a different child with fewer characters to start expanding and exploring. And eventually we would generate all such leftmost derivations of length 5 or fewer, if the query string is of length 5. And we would just have to see, eventually, do we reveal a string that is the query string? So you look at all possible derivations from the start non-terminal with a single step, see if any match the query. Apply all applicable productions to the leftmost variable of each resulting derivation. Reject any derivations that cannot produce the query to help minimize the search space. And we just repeat and repeat and repeat and repeat for every resulting leftmost derivation. The result of applying this is, if the query string is in the language, then we can use this procedure to find it in a finite number of steps. We'll call this brute force parsing. Why does it make sense that this is called brute force parsing?
Because you're trying every possible combination.
Yeah, you're trying every possible combination, and only eventually will you be able to determine that maybe this process terminates. It's called brute force parsing because it is silly. It is the best way that we've seen so far. If we look at the language, if the query string is in the language, it will have a leftmost derivation in a finite number of steps. What are some issues with brute force parsing? There are 2 massive concerns. What are they?
Time cost.
Yeah. Time cost is a huge factor. If we were to apply a complexity to this, what would your best guess to the complexity of brute force parsing? What is the complexity?
Exponential.
It is. It is exponential. What makes you say that it's exponential?
Because it's branching, so.
Yeah, whenever a tree structure is branching, depending on the depth, you have the branching factor to the depth power, and that gives you some kind of exponential complexity. That's absolutely right. What's the other big concern? This one's a little bit harder to see. It's embedded within the language of this. The second to last line here.
Does that have to do with like the leftmost derivation, like from a rightmost?
It's a good idea, but not quite. Good idea.
Are there any grammars that could get a parse tree stuck in a loop? Where it's
Yes.
just like A, B, like non.
I mean, we just look at the last one, right? This A can be produced into a B, which can become an A, which can become a B, which can become an A, which can become a B. Now, what's nice about this is it's producing terminals as we go. So this will eventually terminate as long as we include the rule that as soon as we produce something that's longer than the query string. But yeah, you can absolutely get stuck in a loop that a non-terminal produces another non-terminal, goes back to the first non-terminal in such a way that you do not produce any terminals. So the guarantee that we get from this, or the issue, is that if it's not in the language, then we have no idea whether or not this process is going to terminate or not, at least unless we can look at the grammar and try to figure out, is there an embedded loop in this grammar? And that's easy enough if there are 4 productions in the entire grammar. But if you're looking at something like the Java grammar that I showed you on the first or second day of class, is there a loop in there? Who knows? It would require a lot of analysis to figure out. And if the process doesn't terminate, we can't ever answer no to the question. We can only answer yes, which is really weird. At any particular point in time, we don't know, have we just not found it yet? Or is it not in the language? And if it's not in the language, we will never be able to answer that question, which is kind of scary. So if we can disallow grammar productions of these particular bad forms, then we would be able to know for sure that this process is going to terminate. So as mentioned, there are going to end up being restrictions on context-free grammars, but they're going to stem from these kinds of concerns and not whether or not the grammar is too complex for the language class. So to be able to talk about a regular language, we needed some constraints on the grammar productions to be able to say that, all right, if we can generate a grammar in this form, then it's regular. If we can't, then it may not be regular. Now, we have some concerns about inefficiency. We have some concerns about termination when asking the membership question. So that's going to be what keeps us from getting to be completely and totally creative as we make our context-free grammars. So we're going to disallow productions of these forms. Any non-terminal to lambda. Can't do it. Any non-terminal to another non-terminal. No, this is just another non-terminal. If it's a more complicated expression than that, it's fine. But we can't have something like B arrow A. A arrow D. There needs to be something more than that in the production. Because these are what produce loops, and these are what allow us to go from a non-terminal in the grammar to nothing in the output. If we disallow this, then every non-terminal must become at least one terminal. Which allows us to much more easily see if a particular set of productions is eventually going to become a roadblock. What's important in doing this is that this does not reduce the power of the grammars that we can produce. Anytime we can use either one of these rules, we can also not use them and come up with an equivalent grammar. So we will talk about exactly how to do that. There are a couple of normal forms that we will eventually talk about that do not use these rules and help us to be able to produce very nice grammars that represent context-free languages. If we also get rid of these kinds of rules, then we will also ensure that a brute force membership parsing question will terminate even if the string is not in the language. This can no longer spin its wheels and be infinite. And in fact, we can show that the following rule also applies, proof omitted, of course. The number of leftmost derivations, the actual depth of the tree that we get down to, must be less than or equal to twice the length of the string. So if we have a string that is 5 characters, in the absolute worst case, we will need to be at depth 10 in order to have produced that. If we're deeper than 10 into the tree, then there's no way that particular path can produce the query string. So this helps, but it doesn't actually reduce the real complexity, the actual complexity class. This is still exponential, which is a problem. So computational complexity of brute force parsing, with each leftmost derivation, we will multiply the current number of potential derivations by the number of productions in the grammar. Because at each one of those steps, we may have to, in the absolute worst case, apply every single production. At most, 2 times the length of the string repetitions of that process. So we get the number of productions in the grammar to be 2 times the length of the string W in the worst case. It's not usually that bad, but it is still exponential. You can tell this is my language because it is highly informal. Anything with exponential complexity is just gross. So we absolutely are going to need a method that is more efficient if we want to answer this kind of question for any reasonable length string. If we're searching for something of length 5, this is fine. If we're searching for anything much bigger than 5, this is going to start becoming a problem. There is a length of W cubed method that exists. It is complicated, and we will go over it. In fact, this will turn into your first project, your first potential project in the class. So there is a project in the class, you get a choice of which project you're going to do, and I will reveal the potential projects as we start going over them. This will be the first potential project that you'll get the opportunity to implement, and it's actually quite fun. It's a dynamic programming problem that utilizes something you've seen before in algorithms, but applied to something that is different and real and can solve real problems, which is excellent. There are also linear time methods that exist for very important special cases that have very big restrictions on them. So depending on if we can narrow the problem space down into a very small problem, we can parse that very small problem much more efficiently. But in general, the best that we have shown how to do is a length of the string cubed. Does that seem better than exponential? Have we gone over the rate at which these functions grow and just be able to see the difference between them? It's pretty intense. Using something like a length 10 string, we're just going to call this P to the length of the string W, not 2 times the length of the string W, just for a very quick look at the efficiency. So the difference between 10 cubed versus, I'll use 2 here just because something of base 2 is much easier to show. Yeah. I know it's not quite the same, but we'll get a chance to see how bad this is. In fact, let's just do it with quadratic. And then you can play around with it at cubic and see that it's not actually that much worse. But 10 squared versus 2 to the 10th. What is the ratio of how much faster one will be than the other? Approximately. The reason I do 2 here is because 2 to each power of 10 is approximate, but I like to visualize 2 to the 10 is about 1,000. Which means 2 to the 20th is about 1 million. 2 to the 30th is about 1 billion. You do not want to use this in any program, but if you're just doing some mental calculations, you can, for each power, for each additional 10, you're going to multiply the associated by the 1,000-ish, which gives you the next big number, million, billion, trillion, quadrillion, etc. So 2 to the 10th is 1,024. 10 squared is 100. What is the associated ratio there? 10 times. That's not awful, right? If a program takes 10 times longer to run, that's not the end of the world. Especially when it's this low, it's going to be near instant and near instant. But all right. So what happens if instead of 10, we use 100? What is the associated ratio now? Now we're just looking at strings of length 100 instead of strings of length 10. How frequently do strings of length 100 show up? Frequently. After we do this, we'll think about what happens if we're trying to like compare the genome project, the human genome project, using an exponential complexity algorithm. So first of all, what is 100 squared? That one shouldn't be too bad. 10,000. What is 2 to the 100?
300 zeros.
So if 2 to the 10 is 3 zeros, then 2 to the 100 should be 30 zeros. So 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4, 5, 6, 7, 8, 9, 30. I draw it out because it's stark. It's a stark contrast. If we divide this by that, we get to cancel 4 zeros. It's that many times worse. So anyone know how to say this number? Thousand, million, billions, trillions, quadrillions, quintillions, sextillions, 100 septillion times worse. Does anyone get a sense of the size of the number 100 septillion? Does that, can people visualize 100 septillion? It's kind of hard. Let's imagine that we can factor out the number of people on the planet Earth, and we're going to over approximate there are 10 billion people on Earth. So if we could get rid of 10 billion, there's 1,000, million, billion. We're getting rid of all of these zeros to be able to say every person on Earth. And now we have to redo our commas. Million, billion, trillion, quadrillion. Every person on Earth. 1 quadrillion calculations. If you were able to parallelize this to everyone on Earth, it would still take 1 quadrillion. And what's nice about 10 billion is you can also say, you know, a supercomputer might work at 10 gigahertz. This would still be 1 quadrillion calculations or 1 quadrillion seconds for a supercomputer that was able to do that. The idea is it's just not happening. It's not happening in anybody's lifetime. It's probably not happening before the Earth is what, consumed by an expanding sun as it becomes a red giant. It's just infeasible. And all we did was go from 10 to 100. And 100 is not a big problem. So the difference between anything polynomial and anything exponential just quickly, very quickly becomes horribly infeasible. So I'm sure again you saw that and were told that. I just wanted to make sure that it's very, very clear. Whenever we have an exponential problem, the answer is just no. It's not good enough. All right, so we're going to start working on the problem, but to do so, we're going to need to define some additional concepts. So we're going to now differentiate a regular grammar from a simple grammar. We're going to define this concept of simple if it has productions in one of these forms. Every non-terminal goes to a terminal paired with 0 or more non-terminals. And one more rule, any particular pair of non-terminals to a particular terminal appears at most once in the grammar. So we can't have two different productions that go from the same non-terminal to the same terminal. You can't have two different ways of doing that. There can only be one way of replacing a particular non-terminal with a particular terminal. Given those definitions, is this grammar simple? Three productions, S can be replaced with the terminal A followed by the non-terminal S, or the terminal B followed by the non-terminal S followed by the non-terminal S, or the terminal C. Simple or not simple?
Simple?
It is simple. Why is it simple? Every non-terminal goes to a terminal followed by 0 or more non-terminals, right? The terminal is the first thing that appears. And there's no such pair of non-terminal to terminal pairs. How about this?
Yeah.
This one's actually no, and the reason is that we have two different SS's here. So the way that we derive this will end up being and producing lack of simplicity. So we can't have these pairs of non-terminals paired with a different terminal. So the ASS and the BSS creates a problem.
Yeah, of course.
So the reason we care about the concept of simple grammars is that this allows us to describe features of programming languages. And we'll get into this as we start talking more about compilers, but simple grammars end up being very important. And any grammar you can write in a non-simple way, you can write also in a simple way. I think we have to stop here for the day. I know there was a lot thrown at you today. We'll keep it coming tomorrow.
They're not getting it. This is my.